So 2.7 is all about graphing. Today we're going to cover those first two sections, and then Tuesday we'll go over the next two. But basically just graphing.
Do you have your first attendance too? Oh, they're both coming.
Let's take a look. First idea here is about reflections, also known as mirror images. Now here it's saying red is a reflection of purple, but you could also say purple is a reflection of red. It works both ways. And this is across the y-axis. It could be across the x-axis. It could be across any line. It doesn't have to be one of the axes. So if I had let's just say I had this line right here. I might have something up here, and its reflection would be across that line somehow. So it would be what's maybe like that. So it could be that slanted line that you've got the reflection across. It doesn't have to be an axis is all I'm getting at. Not much of a drawing, but I hope it gets the point across. All right, so first thing is this. We've just got some function y. And let's suppose I do want to reflect it across the x-axis. Here's what I do. Suppose I want to reflect it across the y-axis. Here's what I do. Move that down just a little bit. So let's look at these two things. The top one up there, A, says if I want to reflect something across the x-axis, notice what that's saying. It's saying for every y value above the x-axis, I want a corresponding one below. So if I had these little points right here. Now remember, this is across the x-axis. If I just had those 4 points and I wanted to reflect them across the x-axis, think about it. I would take each one's y value. I'd keep the x value, but I'd take each one's y value and just make it on the other side of the x-axis. Right? So that's all that's saying. It's saying take your function, put a negative sign out in front of it. And that'll give you the reflection across the x-axis. And by the same token, if I want to reflect something across the y-axis, here's some points over here. I would take each one. Now what am I doing? I'm leaving the y values the same, but for each x, I want the negative version of x coming across here. So each pair of those points the y values are staying the same for each pair. What's changing? The x values. Does that make sense? The top one, what's changing? The x values are staying the same for each pair, but the y values are changing. All right? So let's just start off with our old buddy, y equals square root of x. So just think of it, these are all the x values from 0 to infinity. That's the domain. If I want to reflect that across the x-axis, what do I want to change? The x values or the y values? Right, the y's. So I'm just going to stick a negative out in front of that square root of x, and it looks like this. It's saying for those same x values, just make the y's the opposite of what they were going to be. And if I want to reflect that same function across the y-axis, I'm going to say what? Well, the x's are changing because they're on the left-hand side of the y-axis now. I want to leave the y's the same, but change the x's. So now notice I'm sticking that negative sign inside the radical. That doesn't necessarily mean we're trying to find the square root of a negative number. It just says whatever x is, take its negative value. So right here, where it's saying x is -1, I'd have the square root of -1, which is the square root of 1, which is 1. And so I'm getting that point right there. Mirror image across the y-axis. So that's a function we know, and I think it's a pretty easy example to illustrate the point. Question about that? Pretty straightforward. Let's take another one of our functions. Here's the cube root of x. And if you'll jot this down, then we'll try and solve these. The homework's going to ask you to do something similar. So let's take the first one. I want it to reflect across the y-axis. That means I want my y's to be the same. My x's change. So I'm going to say what? Y equals the cube root of -x. I'm taking that function and just every place there's an x, I'm putting a -x. And for the second one, I'm reflecting across the x-axis, so I want my x's to be the same, but each y above the axis, I want it to be below the axis, so I'm going to say what? Y equals negative this whole thing. And so if my y, originally, if my y were going to be 10, now it's going to be -10. That's all that's saying. Are we good? Anybody have a question? Let's do another couple. All right, so I sketched the little original graphs there. So on example 4, we're dealing with the absolute value of x. I want to reflect that across the x-axis. What do I do? In front, okay. So I've got y, maybe not, I've got y equals negative absolute value of x. So wherever y would have been above the x-axis, this is going to put it below the x-axis. So, thank you, Henry. So I'm going to have something like this. All right, so then on example 5, just have a parabola there. I want to reflect it across the x-axis, so what do I do? Thank you. So I've got this. I'll just put the negative sign out front again because I'm saying whatever the y was going to be, make it the opposite. And so then I'm going to get corresponding little thing down here. Okay, let's look at that in a slightly different context. Same idea, but this. You don't have to write this down. Just think with me here. If we look over here on the left-hand side, these are mirror images of each other, reflections. But if you look at the blue graph and the red graph, they are symmetric around this y-axis. What's changing there, the x's or the y's? The x's. So right here I've got some value of x. On the other side, I've got negative that value of x. So if we want symmetry around the y-axis, all that's changing are the x's. That's another way of saying what we just said. And if you look at the one on the right, the blue one and the red one are mirror images, so they are symmetric about the x-axis. What's changing? Well, just the y's. Because here, whatever y is, I want the negative version of it here. So for those 2 points, the x values would be the same. So on top it might be 3, 5. That point might be 3, 5. Down here, the corresponding symmetric point would be what? 3, negative 5. Over here, let's take this point right here. It might be 2, 4. The corresponding point on this side would then be what? Negative 2, 4. The y's would stay the same. So same idea, just now we're talking symmetry, because that's what a mirror image is. But look what it's saying down here at the bottom. Here's the important stuff. If you want to check for symmetry around the y-axis, just replace x with negative x and see if you get the same equation. This is saying to check, you replace x with negative x and see if you get the same equation as what you started with. On the bottom it says, if you want to check for symmetry around the x-axis, replace the y's and see if you get the same equation. Okay, let's put that into practice here. Let's see what one looks like. First of all, is this a function? How come, Bailey?
Because you're getting 2 answers for y.
Yeah, great answer. So if we solve for y, I'm going to get a plus version and a minus version, and that's going to give me what? 1x with 2 different answers for my output. Okay, so not a function, but nobody said that any of these had to be a function. So let's test symmetry about the x-axis and y-axis. So first of all, let's see if it's got x-axis symmetry. So what do? I leave the x's alone, and I replace the y's with negative y. Notice that's all I'm doing here. Okay, so I've got x equals negative y times negative y gives me y squared. Is that the same as what we started with? Yes, it is. So I can say, well, I think I've got x-axis symmetry. Because I replaced all my y's with negative y's, and I got the same equation as what I started with. So, x-axis symmetry. Then we'll check for y-axis symmetry. So, what do? I replace the x's with negative x, leave everything else alone. Is that the same? Nope, it's not. So, no y-axis symmetry. So we're dealing with something that has x-axis symmetry but not y-axis symmetry. And if you think about it, then this picture makes sense. Got this picture off of Desmos, which is one of the neatest things you can use for math. I know you've seen it before, but it's neat just to get on there and play around with stuff. It sure expands your understanding. All right, so we've got something that, like Bailey said, is not a function, but it's got x-axis symmetry. Let's do another one. Function? Yes, it is. All right, so let's try x-axis symmetry. So I changed my y's. So I've got minus y equals x squared plus 3. Leave everything else alone. Does that look like what we started with? Nope. So no x-axis. Let's look at y-axis symmetry. I'll leave my y's alone. Change my x's to negative x. Negative x times negative x is x squared. That looks the same as what we started with, so I know that I've got what? Y-axis symmetry. Now we can look at that and go, okay, that's a parabola. That makes sense. It's symmetric about the y-axis. Here's a picture of it. Can you look at that picture and compare it to the equation and figure out what that 3 is doing? Right. It's just moving that whole graph up 3. That's what we're going to be talking about Tuesday. We're translating that up 3. When I say it's our parent equation, x squared, right? Y equals x squared. We're just translating that up 3. Okay, let's keep going. Function? How come, Peyton?
You put 1x in, you get 1y.
You put 1x in, you're going to get 1y. It's just, anytime you just have plain old x and plain old y, that's a straight line, right? So we know it's going to be a straight line. What do you think about symmetry before we even test? Just picture a line cutting across a graph. Be thinking, let's test here. So we'll test for x-axis first. So I put 2x minus a minus y. I got 2x plus y equals 6. No x-axis. Let's check for y. So I've got 2 times negative x minus y equals 6. So I've got negative 2x minus y equals 6. Now that's what we started with, so no y-axis. Here's a picture. The only kind of straight line that you would have any kind of symmetry with would be either a vertical or horizontal line, right? A vertical line would have x-axis symmetry and a horizontal line would have y-axis symmetry. But this one definitely has neither. Maybe another example? Anybody know what this is going to be the graph of? So I'll test for x-axis, so I leave my x's alone. Put negative y in here. Negative y times negative y is y squared. That one works. So I've got x-axis symmetry. Check for y-axis. So I'll change my x's now. Negative x times negative x is x squared. That looks the same. Here's the picture. Now notice, if this were on a piece of paper and I took the y-axis and I folded along that y-axis, in other words, y-axis symmetry, the right-hand side would fold over and lay right on top of the left-hand side. And by the same token, if I took the x-axis as my fold line and folded along it, the top half will match exactly with the bottom half. All right. If you'll copy this down, please. We're getting pretty close to the end of the notes here. Okay, symmetry with respect to the origin means, let's go back and look at our circle. It means if I put a pin right here at the origin, and then just picked a point on that circle. Let's come up here. If I made a spinner out of that and rotated 180 degrees, would that graph look exactly like it does now? If I turned the whole thing 180 degrees, it would look exactly like it does there. That's what symmetry with respect to the origin means. You put a pin at the origin, you spin it around 180 degrees. If it looks identical to what you started with, you've got symmetry with respect to the origin. All right, and then here's what the textbook says. Again, don't write this down. It's in the book, which I know everybody's reading. Here's the important stuff. You can check for symmetry with respect to the origin by doing both of these things. Replace x with negative x and y with negative y. If what you get is what you started with, it's got symmetry with respect to the origin. Now look at that first part there. If you replace x with negative x, isn't that what we used to check for symmetry around the y-axis? And if you look at the second one, y with negative y, that's exactly what we did to see if it was symmetric around the x-axis. So in other words, if you've got y-axis symmetry and x-axis symmetry, you have to have symmetry about the origin. Did we have that back here? Yeah, let me do this. That circle has x-axis symmetry, it has y-axis symmetry, therefore it has symmetry about the origin. Okay, we're getting there. Let's try one here. I want to know if it's got symmetry about the origin. We've got two last examples here. Here's example 7. So the first thing I'll do is I'll check for, I'll just do it both at the same time. So I'm going to replace y with negative y. I'm going to replace my x's with negative x. Just test for both at the same time. So I've got minus y equals negative 4. Now then, negative x cubed means negative x times negative x times negative x, which is going to give me negative x cubed, right? This is not looking like it's going to work out, right? So I've got minus y. Negative 4 times negative x cubed is 4x cubed minus x. Do I say it's not symmetric about the origin? Anybody compare that last line in the red to what we started with? Notice anything?
Both by -1.
Excellent. So I'm going to divide both by -1, both sides, or each term. So I get y equals negative 4x cubed plus x, which is what we started with. So I could say, yeah, that's got symmetry about the origin. Now here's a question. Stop writing for just a second. Does that mean it's got symmetry about the x-axis and symmetry about the y-axis? Let's look back. Here we said, if it's got symmetry about the x-axis and also symmetry about the y-axis, it's got symmetry about the origin. Is the opposite true? Nope. Now look at that. That's the graph of our original equation. It does not have x-axis symmetry. It does not have y-axis symmetry. But it does have symmetry about the origin. If I put a pin right there and I spun that thing around 180 degrees, it would look exactly like what it started with. So you can say, if you got x-axis symmetry and y-axis symmetry, if you got both of those, you've got symmetry about the origin. But you can't say, oh, if you've got symmetry about the origin, you've got both those others. That's not necessarily true. Here's an example where it's not. All right. Last example. Strange looking little critter. Take a guess what you think about symmetry about the origin. Think so? So I'm going to test for both at the same time. So I've got negative y. I've got negative y squared minus negative x squared equals 1. Negative y times negative y squared minus negative x times negative x. So it looks like it's got symmetry about the origin. If there was a plus in between those two things, I'd have a circle with radius 1, but there's a minus in there. What in the world is that graph going to look like? I know it's got, if I can rotate it 180 degrees, it's going to look the same, but what's it going to look like? This. If I put a pin right there and rotate that whole thing around 180 degrees, it would look identical. So yes, it does have symmetry about the origin. In this case, does it have symmetry about the x-axis? Yeah. Does it have symmetry about the y-axis? Yeah. If you made fold lines on the x-axis and the y-axis and folded, those different pieces would hit on top of each other. But just because it's got symmetry about the origin doesn't necessarily mean that it's got x-axis and y-axis symmetry.